Let me first show you the cluster. Running containers is easy. The hard part begins when the application needs to work across multiple machines. A container image solves packaging. Docker Compose solves local multi-service execution on one machine. But once we spread an application across multiple machines, the problem changes. Now we care about placement, recovery, capacity, and the service discovery. Docker Compose does not manage those fleet level concerns. Kubernetes does. Today, I'm not going deep into Kubernetes architecture. We are not unpacking API server, scheduler, controller, kubelet, or etcd. This episode answers one narrower question: why does Kubernetes exist? My name is Arbaz, and I've spent more than 12 years working across DevOps, cloud, and platform engineering. I created this production cloud native platform series to show how infrastructure tools emerge from real operational pressure using application called Shopflow as the story we keep evolving. If your company builds around Kubernetes, cloud infrastructure, observability, security, platform engineering, or the CNCF ecosystem, and you are interested in sponsoring or collaborating, you can reach me through my email in the description. In the last episode, Docker and Docker Compose were not the problem. They were useful right up to the point where orchestration became the real issue. We saw that multiple replicas on one single host share one failure domain. Deleting the replicas does not recreate it automatically. Several Docker hosts do not become one cluster by themselves. Service discovery across host becomes manual. Node failure requires human discovery. Scaling becomes a sequence of commands instead of a declared state. Version coordination became manual. Kubernetes exists to solve that orchestration layer. And today, I want to prove that through behavior, not theory. For this session, I am using a lightweight disposable Kubernetes environment with one control plane node and two worker nodes. This is not the final production cluster for the series. Right now, I just want a clean environment where Kubernetes can show us the behaviors we could not get with plain Docker tooling. The important shift is conceptual. In episode 4, we had separate machines and we operated them individually. Now, Kubernetes sees them as one cluster. I'm no longer thinking in terms of SSHing. I am declaring a workload, but that is a separate topic. The big point is simple. Multiple machines are now presented to us as one scheduling domain. I am not migrating the entire Shopflow platform yet. For this session, I only need a small workload that clearly demonstrates the orchestration behavior. So I am reusing the existing Shopflow backend because it already exposes health endpoint, ready endpoint, and API instance endpoint. The API instance endpoint is especially useful because it tells us which replica answered the request. Notice what changed compared to the Docker world. I did not log into individual machines and choose where each backend should run. I declared that I wanted 3 replicas and Kubernetes handled the placement. If you are wondering how the scheduler makes those placements decisions internally, we are going to unpack that separately. The operational difference is the point. Manual placement became cluster scheduling. This is one of the clearest demonstrations of why Kubernetes exists. In episode 4, when we removed a backend replica, nothing recreated it. Desired state said 3, the actual state became 2, and a human had to repair that gap. Now, watch what happens in Kubernetes. I'm going to delete the pod real quick, followed by I'm going to run this pod, and if you see the readiness state is, let's say, 0 and /1. Once again, if I run, it automatically is running. One pod is removed. For a moment, the actual state drops below the desired state. But Kubernetes does not stop at that broken moment. It continues reconciling towards the declared replica count. So a replacement pod appears. This is the beginning of self healing. Not because Kubernetes is magical, but because the platform is continuously trying to move actual state back towards the desired state. We will go much deeper into the control loop thinking later. Today, the important point is manual recovery became automatic reconciliation. Next, let us scale the workload. In episode 4, scaling across machines meant deciding where each workload should go and then performing the placement manually. Here, I simply declare a new desired count. That is the operational shift. I am not choosing 6 target servers manually. I am not running 6 independent Docker commands on multiple hosts. I am declaring the desired size of the workload, and Kubernetes decides how to place those pods across available nodes. Manual scaling became declarative scaling. And if you are already wondering how Kubernetes decides where they go, that is the right question. We'll answer it properly later. In the last episode, cross host service discovery became manual. We had to care about specific workload addresses, specific machine roles, and manual upstream configuration. That becomes fragile as soon as workloads move or get replaced. Now, I want to introduce a Kubernetes service. The client is no longer calling an individual workload IP. It is calling a stable service name Shopflow backend on port 8000. That service remains stable even while pods are replaced underneath it. Changing workload IPs no longer force every client to track those changes directly. Manual service discovery became a stable service abstraction. We will explore how service networking works in more depth later. Right now, I want to stay focused on the problem it solves. Now, let us make repeated requests to the service and see which backend replica responds. I am repeating the same request because API instance tell us which backend answered. This makes the platform behavior visible. Clients keep using one stable service endpoint while cluster distributes traffic across multiple healthy replicas. That is exactly the kind of coordination that became manual and fragile in the last episode. This is where I want to show a real node failure instead of only talking about it. I start with a healthy cluster, then I intentionally take one worker out of service. This is the important behavior to watch. Draining a node tells Kubernetes to evict the pods from that node. Kubernetes then recreate those pods on healthy capacity if the deployment still wants them and the cluster has room. Later, if I bring back the node, that does not mean Kubernetes is constantly rebalancing healthy pods in the background. It means the node is available for the future scheduling again. So the lesson is simple. Kubernetes responds to desired state and node health, but it does not reshuffle running pods just for the sake of event distribution. This is also a good moment to clear up common misunderstanding. Docker and Kubernetes are not direct replacement for one another. Docker and container tooling solve packaging and running containers, orchestration across infrastructure. Modern Kubernetes commonly uses CRI compatible runtimes such as Containerd, and it does not require Docker engine itself. So the point is not Docker is bad or Kubernetes is good. The point is that containers solve one level of problem and orchestration solves the next level. Let us map the pain from the last episode directly to what we just saw. Manual placement became Kubernetes scheduling. Manual replica management became a declared replica count. Manual recovery became automatic replacement after pod loss. Independent servers became one cluster. Manual scaling became declarative scaling. Changing workload IPs were hidden behind a stable service. This is why Kubernetes exists. Not as a badge, not as a trendy technology, not as a generic interview topic. It exists because operating distributed containers workload manually does not scale. Kubernetes is powerful, but it's not magic. It does not automatically solve application bugs, database architecture, backups, observability, security policy by design, cost management, networking design, GitOps workflows. Those become future platform concerns in this series. Kubernetes solves orchestration problem. It does not remove the need for engineering. Today, we used Kubernetes in the smallest meaningful way possible. We did not build the final production cluster. We did not migrate the full shop floor system. We did not dive deep into the internals. Instead, we answered one practical question. Why does Kubernetes exist? It exists because one application run across multiple machines. We need a platform that can schedule workloads, maintain desired capacity, restore missing replicas, give us stable service discovery, and also coordinate distributed execution without turning operations into manual server by server work. We take the logical step and ask how Kubernetes is actually built to do that. That is where Kubernetes architecture begins. Thank you for watching. I'll see you in the next video.